It's a great pleasure to introduce Matt Jones from Princeton to talk about images of mathematics, realities of mathematics in AI.
Thank you to the organizers, Adrian and Ursula and the staff here, and all of you for providing such food for thought. One of the things about going last is that we've had so much to talk about that my talk has been protean, so if it has filled with misspellings, I can blame that. Unfortunately, ChatGPT was down yesterday, so I don't have a talk. But so I wanted to begin with a question of poor training data. And since you're mostly an audience of historians of mathematics, you'll know who Terence Tao is. And Terence Tao has recently come into some criticism and celebration as a great pure mathematician interested in generative AI, large AI models. And in an interview he did, initially in a German periodical, he says, part of the problem is that that is the large language models, doesn't have enough data to train on. There are published papers online you can train it on, but I think a lot of the intuition is not captured in the printed papers and journals, but in conversations with mathematicians, in lectures, and in the way we advise students. Now, every historian and sociologist of the sciences just cheers with joy about this. He says, sometimes I joke what we need to do is to get GPT to go to standard graduate education, sit in graduate classes, ask questions like a students, and learn like humans learn mathematics. In other words, the blackboard, this is the blackboard in the men's room over there, incidentally. It now has joke. Okay. That somehow this is more important than that, or at least is necessary, and see Barani and Mackenzie. Now, I think this is extraordinary in so many ways, and we could have an entire discussion about the conditions under which statements like this are made in different scientific communities. But I'm interested in precisely the way in which the coming to be of the certain kind of large language models, now called AI, invokes this kind of self-reflection about the nature of disciplines and about training. And I'm interested in the way, particularly at this moment and then in earlier moments, how efforts to automate or emulate mathematics reveals precisely the kind of gulf that he's talking about. The gulf that's the lifeblood of a non-anachronistic, non-Whiggish history of mathematics and other kinds of sciences, where there's a division between the working practices of mathematicians and their various rational reconstructions, whether it's a romantic history, old bad philosophy of math, or logical reconstructions, right? And it's also very productive. And this is a theme that I think is enormously important in the history of mathematics, and it's also important in the history of computer science, as we've just heard in the unbelievably wonderful work of Professor Dumont, is that the effort to give forms of emulation, efforts to automate, efforts to transform that reveal this, produces new forms of human and machine practice. I think this is true of machines. I also think you could arguably say this about things like moments of axiomatization, other sorts of things. So I think this is a really interesting moment. So there's a major irony in the fact that Tao is using the new kinds of artificial intelligence and talking about it. Because the form of machine learning that has now come into the centrality that we hear so much about, that has been rebranded AI, is premised quite precisely on the rejection of the mid-20th century understandings of intelligence that were grounded in logic, in more axiomatic conceptions of mathematics, and the image of intelligence that people that excelled in those sorts of things. So this is quite striking. So now, ironically, in the hands of Tao and other people doing automatic proof, this form of machine learning, which, as I say, is premised on the rejection as a method of a form of artificial intelligence grounded in logic, is now seen as a way of realizing the production of formal proofs that, as we all know, mathematicians don't actually do most of the time in an automatic way. Now, this irony gets even deeper. Now, this is a paper I cite this all the time, but usually to audiences that don't get the reference. You all know the reference, and it was cited the other day. So some years ago, 3 researchers at Google wrote a paper called The Unreasonable Effectiveness of Data. It was an explicit repost to the papers you all know very well. An explicit repost to the idea that there was something about the effectiveness of pure mathematics which seems so profoundly disconnected from the world. And instead, they advocated a really kind of radically different epistemological program connected to a vast effort of computing. And they write, explicitly talking about sciences of human beings, they write that sciences involving human beings are resistant, as they say, to, quote, elegant mathematics. We're not going to have the elegance of physical equations. We're not going to look like the standard model. We're not going to look like anything. We should, he says, Norvig and others, we should stop acting as if our goal is to author extremely elegant theories and instead embrace complexity and make use of the best ally we have, the unreasonable effectiveness of data. This is at the heart of the current model that is in AI. And they call, moreover, for an explicit celebration of memorization. They write, it's a good policy to have a lot of training data. And they write, for those with experience in small-scale machine learning, or they also mean traditional statistics, who are worried about the curse of dimensionality and overfitting of models, the experimental evidence from the last decade says throwing away rare events is almost always a bad idea. Could spend the entire next 40 minutes talking about these sorts of transformations, but actually I think this is precisely the audience that reads this and knows exactly what's up. Now, they're pushing, the paper is about language models, and it's an explicit attack on the Chomskyan program, where famously colorless green ideas sleep furiously, is statistically highly improbable and grammatical in English, and was Chomsky's attack on the behaviorist and statistical approach to language. Norvig et al.'s approach with data is to say that the Chomskyan program and the entire array of high modernist forms of scientific knowledge that we heard about a little bit in Alma Steingart's wonderful book on modernism and mathematics, but is central to so many forms of structuralism, up and including Thomas Kuhn's paradigms, are to be discarded. That is, a moment in which a whole slew of high-century modernist approaches are being overthrown. Okay, so what I hope this makes you get a sense of, if we want to think about this moment of AI and its intersection with the history of math, that the history of math is very important in thinking critically through many of these things. And the history of AI is actually helpful in thinking about the history and philosophy of mathematics. So I am going to talk too quickly and too briefly about, first, I'm just going to tell you a sort of brief history of how this transformation happens in AI, or at least one facet of this. Then secondly, I'm going to talk, and I truly am introducing this to you with not a huge amount of knowledge because I think it's interesting. It's a set of problems that we and our students ought to look at about mathematics in response to the kinds of things that Norvig and others are celebrating, to large language models. And then finally, I want to come back to thinking about how do we do history of automatic machine learning and AI in mathematics itself. Now, I went to the archive when someone's paper was canceled, so I ran over to St. John's and looked at the Maurice Wilkes papers. And they are amazing, and everyone should go. Now, he over and over again has a long thing about how von Neumann took all the credit for the von Neumann machine, something that modern historians more or less agree upon. But I loved this and had to share with you. Mathematicians tend, I like it misspelled, mathematicians tend to overestimate the importance of mathematical insights. This has been a major move in the history of computing, and it's both true and super problematic. But it becomes more problematic the more we recognize, as we've been talking, that mathematics does not equal or turn into logic, despite lots of people sort of wanting that, and that's part of the productivity of it. And just to follow up the previous talk, and thinking methodologically, I think the way to not dumb down the history of computing and math via anachronism is that we need to be meta-technical, not technical. We need to talk about mathematics plural, logics plural, formal plural, tool plural. We need to open up a lot of black boxes. And I maintain this is something that historians of mathematics who are willing to entertain the non-identity of mathematics over time and yet work hard at things that are formally difficult are really poised to do. Okay, so my three inquiries, I'm going to start with mathematics in different models of machine intelligence. Now, I'm going to do a very quick and hand-wavy story of artificial intelligence, particularly before the current moment. And I do not claim to do this well. As Ursula said, much smarter people than me will be telling you about this genealogy. And a variety of us, including remarkable people here at Cambridge, put together an edited volume in the British Journal of the History of Science on varied histories of artificial intelligence. I recommend each of the studies to you, and the introduction, particularly the parts I didn't author, as extremely helpful in thinking through this field. So I'm going to begin in the most classic way possible, which is at Bletchley Park. There's when is the trip to Bletchley Park?
It is March.
March. Okay. At Bletchley Park, in the evenings when all of the women were forced to do exercise, Turing and his friends, Donald Meeke and others, had walks where they apparently talked about the fact that they were surrounded by automation. And they discussed various implications of this, including how they might want to automate chess, but also different ways to think about how it is that you could have machines emulate various kinds of human activity. And they thought both about learning from experience and from reasoning using rules. And this developed both from the two facets of Turing, the famous Turing, the logician, but also the Turing at the heart of not just solving enigma, but being one small cog in a vast machine of dealing with real-time data at a scale unprecedented in human history. So these are ideal types, but they do structure and are helpful in understanding the development of AI. Now, the famous next great figure thing is, of course, the Dartmouth Conference. And the Dartmouth Conference is a group that comes together with varied agendas for what it might be, and it does use the term artificial intelligence. I mention it largely because John McCarthy, a topologist turned a computer scientist, was very explicit that artificial intelligence was always a term for branding and getting money and not something else. Now, one facet, the facet of the program that emerges, and many of you will probably know this better than I, is the so-called realm of symbolic AI. Roughly speaking, in a very trivialized way, that you take something like your model of intelligence, the image of the mathematician, particularly the image of the mathematician refracted through early 20th century conceptions of logic, and you make that the heart of intelligence, and that's precisely what you try to automate. The history of this is almost over-determined, and it's far more complex, and it's just not what I am going to focus on here. McCarthy, just to give you a sense of the approach of this project was explicitly non-empirical in the way so many things were in the middle part of the 20th century. So McCarthy writes, as part of the battles against an over-empirical form of artificial intelligence, the direct application of trial and error methods to the relation between sensory data and motor activity will not lead to any complicated behavior. A less true statement. This is 100% wrong. Whatever you think of ChatGPT, this is totally wrong. When your computer, you scan a photo on your iPhone and it does OCR on the document, like my one from 2 days ago at St. John's, that's very complicated behavior, and it sure as hell is not coming from strong AI. So in McCarthy and a whole variety of people that we could talk about, the sort of data-centric approach was not worth the name, and they spent a lot of time making sure it wasn't funded at the highest levels of basic science in the US, the UK, and other sorts of places. Other people will tell the story. Now, the AI of our past half-decade is, of course, almost the antithesis of this. And to speak really roughly, it emerges from a data-centric approach. It is enabled, and I won't talk about this at all today, by relatively weak privacy and intellectual property protections. Those are in the news quite rightly every single day, coupled to a radical organization of research labor, and I should say computing infrastructures. Tom just reminded me we didn't talk enough about databases in our book, and he's right, joined to unbelievable massive amounts of money. And that only continues. Now, everyone's been doing a little self-advertisement. If you want to get the more technical version of this, you can read sort of my more history of mathy paper on the genealogy of the black box, or you can read our popular history that I wrote with an applied mathematician in interesting ways. Now, if we want to understand this strand, we need to focus not on Turing sort of through his genius dealing with the Enigma machine, but the fact that Bletchley Park and Arlington Station in the United States were massive data-oriented factories. And from them, and in certain other places, comes what I would call a low road of instrumentalized statistics, part of the whole realm of applied mathematics that is sort of non-visible, because it doesn't have the same academic prestige or visibility to us in many sorts of ways, in which there's a combination of vast archives of data, in cryptological in the first instance, but increasingly commercial, and other kinds of military data, plus an extremely instrumental statistical approach, including Bayesian statistics, which is basically was dead everywhere, but very much alive in cryptography. This is amplified by the experience, particularly of extremely good mathematicians who emerged from the Second World War with a sense of the power of applied statistics and data. And John Tukey, who was at Princeton and also Bell Labs and consulted heavily for the National Security Agency, for example, captured this in a paper assailing the statistics profession, mathematical statistics, for being too concerned with mathematical rigor rather than as a form of investigation. Now, I can't give the whole story, and no one has, because what you have is, around the world, rich ecologies for the prediction of of doing instrumental predictions based on high-dimensional, messy data. And these ecologies are super interesting. If there's someone who reads Russian who really wants to look at the most mathematical of it, there's a whole field of automation studies, basically unstudied. I've been trying to convince people. But similarly, France, Japan, the Netherlands, and elsewhere. Now, this takes many forms. And just to give you an example, pattern recognition, which is one of the many names for this sort of instrumental statistics, heavily funded by the US government to deal with satellite imagery such as this. What do you think that is? It's a tank. We all can do this, so can your phone. This was heavily funded and developed large amounts of the investigation of non-parametric statistics and the entire set of infrastructures that were necessary to develop them. I'm rushing through this story very quickly. Now, where did this go? Well, the symbolic AI program that I mentioned before famously survives as a basically kind of undead thing for many years and goes through sort of many winters. This underlying low road continues sort of unabated. And it comes into a greater centrality in the 1980s and early 90s. And it does so as part of a mutation in the hubris of artificial intelligence. By the 1970s, efforts to produce general intelligence had given way to what were called expert systems. But expert systems had turned out to be at once possible in very limited domains and extremely hard. And one of the reasons it was so hard is that the computer scientists doing this discovered something at the same time, the people in the sociology of knowledge and of science, that it's really hard to characterize human knowledge in anything like the way that all the logicians and analytic philosophers had told us we were supposed to. So for example, and this is just a random paper in a 1991 volume funded by NASA, human experts find it difficult to express their knowledge in terms of concise situation action rules. Yeah, Harry Collins, same thing. There's a history to be written about why this realization. In AI, this is called the knowledge acquisition bottleneck. So the idea was that it was going to be really easy to extract knowledge from people, and it turns out to be really hard. So this is an example at the Stanford Research Institute funded by DARPA, and it's a whole discussion with a lathe maker, and it's like the most ethnographic thing possible. It's unbelievable. It's like the sociology of science being done in real time at the same time down the street. People are thinking about this kind of stuff. It's amazing. Donald Meeke, a major computer scientist whose papers are at the BL, amazing, amazing guy. He hung out, it was a very junior person at Bletchley Park, was very reflective about this. And here comes to the image of mathematics. He wrote, and this is in 1985, mastery is not acquired by reading books. It's acquired by trial and error and teacher-supplied examples. This is how humans acquire skill. People, which people? Well, certain kinds of academics, right? Are very reluctant to accept this. Their reluctance tells us something about the philosophical self-image that we, as human beings, prefer. So a philosophical transformation in the nature of the image of the knower is at the heart of what is becoming machine learning. Now, what develops out of this is what is known now as supervised learning. And basically the idea is this. If you want, say, to work through millions of photographs of the stars, you know, of course, as we know, you did human computers, and you did human computers in the 1890s, and you did human computers in the 1980s. But you want to automate that process given the scale of things that is being surveyed. How do you do this? Well, you can't get people to tell you how they know. But what you can do is have them classify large numbers of objects and then use a variety of algorithms, which I won't talk about unless you want, to predict what it is that people are doing without any pretense of understanding their cognitive processes. And so in this example, the astronomer, which is this box, makes training data. That means the astronomer, he or she, is classifying a large number of stars, and the algorithm is producing a model which will try to replicate that, that classification without overfitting. This is the model of supervised learning. Many different forms of algorithms are proposed, and there's much to this that I could talk about. Now, when this was initially introduced, people still had a vision that eventually this would come to produce rules in a human understandable way. Because that was at such the heart of what it was to know something, and it was such a desire that machine learning ought to produce interpretable things. And so Meeke, who I just quoted, was sort of very worried about this. And it wasn't only in philosophical statements, it was in fact in the code. So if you play with the sort of dominant software for producing what are called decision trees, which are exactly what they sound like, in the late 1980s and early 90s, you can get your results both as a statistical predictive model, or it will produce rules for you that are human legible. This, in some sense, is the last gasp of machine learning producing what we think of as interpretable rules that have been produced through induction over many people's decision making. Because at the same time, what's happening is that both in the machine learning community and in the increasingly computerized statistics community, there comes to be a realization that if you build lots of models simultaneously and you allow them to combine, whether through voting, averaging, a whole slew of techniques, they're going to be more powerful than any one. And this could include running the same algorithm 1,000 times. Something called random forests was the best example, and before neural networks was the best apple. Or it could be a whole slew of different algorithms with very radically different assumptions about them. This, even more so than what I've been talking about, destroyed sort of the image of what it is that you're supposed to have as a scientific object that you're building into an algorithm. And it radically challenged mid-century models, visions of good statistical models, and the relationship to scientific understanding. And this is still reverberating through the scientific community in which machine learning models that do not produce the same kind of causal models or mechanistic models are becoming ever more important, but challenged in, say, tenure decisions. And the key document here is this amazing paper by Leo Bremen, The Two Cultures of Statistics in 2000, which I highly recommend to you. It came into public eye because of something called the Netflix Prize. Anyone heard of this? Yeah. Netflix Prize 2006 to 2009. Netflix made available a really large, for the time, commercial data set, and people were thrilled because people had realized scale really mattered, and yet commercial data sets were not made available. And the Netflix Prize offered $1 million to whomever should be able to get a 10% increase in the prediction about how people would rate movies. Now, it was a massive example of sort of crowdsourcing, and people were very excited about this. And it's an amazing, it's amazing empirically for a historian because it not only happened online, but there were online forums, discussion sorts of things. And what it allows us to see is the dawn of realization on all sorts of people involved in this, from researchers at Bell Labs, undergraduates at Princeton, random people in their garage, that something different was happening in predictive algorithms. So this is from the forum. So someone named Winsteps, if you're Winsteps, please identify yourself. I would love to talk to you. It will be interesting to see whether the winning solution has the neat elegance of Newton's laws of motion or merely an elaborate empirical description of modern equivalent to Ptolemy's epistec. A lot of these people vaguely remembered their history or philosophy of science 101. Not well, but well enough to say this. The winning prize looked like this. 500 predictors combined in multiple ways to produce a 10% improvement. From the perspective of almost all science of all time, this is an ultimate horror. Right? This is awfulness. And yet, this is the state of affairs. Indeed, it captures a moment in which the value of prediction, the epistemic value of prediction, radically overruns interpretability, intelligibility, most of the epistemic virtues that science typically has. Winsteps continues, Newton's laws solved not only the original astronomical problem, but Ptolemy's solution was only good for astronomy. But he was old hat. They also go on and on about Occam's razor, you bet, everything, philosophy 101. So this was a sort of radical transformation in the kind of objects. This is a mathematical object, but it's the wrong kind of mathematical object. And it's analogized to a historically wrong kind of mathematical object. Now, it was not just an epistemic thing, it also involved fundamentally a social organization of predictive capacity. This was, of course, true at Bletchley Park and Arlington Hall in the United States during the Second World War, but all the more so in the world of machine learning. And indeed, the communities come to be organized around this epistemic value of interpretability, but also a common metric that allows you to organize something. And a statistician, Donald Donahoe, has called this the secret sauce of machine learning. You optimize around a single agreed upon a metric that you predict, and an entire community can work. So there's this radical sort of social understanding, despite our lionization of geniuses. Within the community, there's a sense that this is a collective project and succeeds precisely because it's a collective project. Now, just to get us to the present, by 2010, there was a sense that many of the old problems in AI were about to be solved. And there was a competition called ImageNet, which used a set of images that had been labeled by thousands of Amazon Turk workers to try to come up with a visual recognition technologies that could do this as well as human beings. And the competition was won by a form of algorithm that was precisely that which the symbolic AI people so despised, and particularly so-called neural networks. And it was won in 2012. This is now told as a thoroughly teleological history. That it was always obvious this was the way to go, that this should have happened much earlier, that the entire scientific community was blinkered, and that's all completely wrong. This was entirely implausible, even as late as 2009. Why? Now, neural networks were deliberately taken on by the symbolic AI community, but they had plenty of problems. They required truly enormous amounts of data, large amounts of data that was available by 2009, but they also required lots of computer time. They were very expensive, they were utterly inscrutable, so they were entirely the wrong kind of epistemic object, and they were very slow to train. Now, the issue of training them, which the symbolic AI people thought they had killed, well, they hadn't. In fact, the solution, it turns out, is doing the chain rule trillions of times, over and over and over again. So this is the key paper. Recently, one of these people got the Nobel Prize, but essentially using the chain rule again and again to recognize and then change weights on the basis of kinds of error. This was possible in theory. In practice, incredibly hard and incredibly slow to come to any sorts of things. The research barely survives. In fact, tons of people who are famous now leave the field and do other kinds of things. It's kept alive in part by the Canadian Research Fund. Okay, so it's widely seen as not practical until something has changed in the realm of the kind of hardware that's available. So by 2009, the need for ever better gaming and for computer graphics has produced a whole new set of massively parallel forms of processors known as GPUs. This is an example of an NVIDIA 290. NVIDIA was not one of the largest corporations at the time. NVIDIA decided, quite smartly, that maybe their processors could be used for scientific computing and pushed hard for this, never mentioning machine learning. And yet, machine learners began to try to do this and realizing that the kind of massive data computation that they were doing could often be parallelized. This is a wonderful moment for historians of computing and historians of mathematics to work because it's at once dependent on a transformation of hardware, but requires a radically other scheme for parallelizing programming, particularly programming of doing vast amounts of computation, and the implementation in actual running code. All of this happens between 2009 and 2012. And it is exactly this software and hardware, which is both off the shelf, that gets put into place in 2012 with a winning paper that is able to categorize all of these things better than anything else. This moment, neural networks become the new hotness, which they have been since then. And they are triumphed by, in this famous paper from just 2015, they're rebranded as deep learning, and it is presented as obvious that this should always be the case. This itself is what's been recently rebranded as AI, and I use rebranded quite deliberately. Unfortunately, as we're all learning, the vision of this was not going to be a supercomputer on a desktop, but rather the huge data farms that we need to know with the environmental impact. This was not pre-given. Anyone telling you a teleological history is trying to make things easy and easy morals. So this eventually, of course, is the undercurrent of the current world of ChatGPT and foundation models. Okay, so I gave you this history because I wanted you to understand that there's this radical transformation in the image of what it is to know, but it is deeply connected to deep and different kinds of technical results, their implementation on real hardware with data that is produced in sort of all kinds of contexts that matter. Those contexts themselves don't explain it. The computers themselves don't explain it. And the code doesn't explain it. And the math doesn't explain it. But we need them all of those components. And we need to recognize how radically other that kind of math is to understand the moment we're in. That's something that the history of math community is well prepared to do at a really interesting level. Okay, so the remainder of what I'm going to talk about, I'm going to go through much more quickly. So I'm going to talk about mathematics to understand what has been wrought, and then I'll come back very briefly to automatic reasoning. So I promised myself I'd leave room for some. So in the explosion of ChatGPT, with all the conversations we're all having about plagiarism and other sorts of things, there is a really interesting and not studied yet movement to understand how weird everything that's gone on. A lot is non-obvious. Like, for all of our real and appropriate appreciation for how bad ChatGPT is, even in its latest incarnations, nonetheless, it is empirically the case that something happens when you train language models on 10,000 tokens that was unthinkable in the middle part of the 20th century. It's empirically the fact. No one really knows why. The memorization that I quoted from, this turns out to be right to a much greater extent than anyone ever would have been surprised. But another and more technical point is that the point of not worrying about overfitting turns out that there's now ample empirical evidence that producing truly enormous models with billions of parameters on trillions of data points in which you don't have the kinds of predictive loss that you typically have in training statistical models, and this is called double descent. And the idea is that traditionally, in training models, you ran the risk of memorizing your data set and thus being not generalizable. But at some point, many people found, this reversed itself. And all of the traditional worries about overfitting began to not be the case. In some sense, I talked before about the pushing against the traditional virtues of logic, pushing against the traditional virtues of classical statistical models. Here, they're pushing against a very central virtue that's taught to you in day 4 of any machine learning or statistics class about worrying about this statistical virtue. And yet, somehow, this, in many cases, appears to be collapsing. This is an interesting and powerful research program. And it turns out that the fundamental rule that everyone had been taught about how to make models generalize does not generalize. Now, how robust this empirical result is, I think, is entirely up for question. There's a lot of people who have a lot of money dependent on this not being the case. But nonetheless, it's a really interesting kind of problem. And it's a problem in which you're dealing with incredibly large amounts of high-dimensional data. Now, people getting into machine learning, unlike most of us, have not taken real analysis in large numbers of variables. In other words, they've not taken good linear algebra classes. They haven't been trained. They don't have intuitions about what happens to Euclidean distances in spaces larger than 7, right? Those are at the heart of all of this. And so they are calling for mathematicians to help understand why all of this does these sorts of things. Why there's benign overfitting. Why the curse of dimensionality has now become the blessing of dimensionality. And indeed, to explain the effectiveness. And they do so, what is amazing, is they say, look, the mathematicians came after the century of Newton and Leibniz, after the century of Euler and D'Alembert, and set things right. And we need to do this now. I don't know if this is going anywhere. It's profoundly interesting. It's a huge object. And our community is the one to do this. But interestingly, it's doing so for reasons radically counter to the image of pure mathematics and mathematical statistics. Okay, my third part. Machine learning as a tool for mathematical inquiry. So if you go downtown across from Trinity, this is the current state of literature on AI down there. There are more books here than there are in the history of science. And includes many books in the history of science have been reclassified here. I'm quite angry they did not include my book. But there's a certain moment, and these books are of incredibly varying quality. Almost none of them involves people who are truly savvy in having a truly Whiggish history of mathematics. And so I think that is a really great question about what it is that we particularly can do to enrich the conversation. And how can we enrich the conversation differently from all of the ways that people are doing this? And I don't mean to diminish any of this. Like, Microsoft is using a hell of a lot of world to flood the world with AI. It is true. And there are lots of people who are good at talking about environmental history. And then there's people who are saying the AI industry is built on intellectual property theft, environmental destruction, gain support by promising grifters money and students an easy ride to their goal. True. But these are not the only analytical places to go. Already, mathematicians are having the kinds of discussions that people in all kinds of fields are having. And one of the fascinating things is, of course, the self-image of mathematics is in many ways distinct from many of the sciences. It's not accidental that Moore and others had this sense of the humanism of mathematics, and much of the response structurally, though it's about mathematics, looks structurally like conversations that are happening in literature and art and other kinds of things. There was in 2022, there was a symposium, and many of these papers didn't get printed last year, in a remarkable set of essays by mathematicians, a major ethnographer of mathematics, that really are thinking hard about fundamental questions of interest to historians and sociologists of mathematics. And there's ample polemic from my former colleague Michael Harris, among other kinds of stuff. This is interesting. Now, as I already said, it's structurally homologous to the conversation in literature and arts and the humanities. And I think we need to take that seriously in thinking through this. So I often, when I'm talking to humanities audiences about AI, I really want to stress this is not a revivification of science versus the humanities a few years ago, because the disruption, as it were, of traditional expertise is very field non-specific, right? It's about literary analysis and signals intelligence, but also pure mathematics and credit ratings. What is our job for this? Well, I think this has been a really rich moment, but as historians of mathematics, what are we able to do? Particularly if we pluralize mathematics and we get beyond nostalgia and Whig history. So our job, as I take it, is precisely the radical historicization of proof standards, training institutions, practices, and technicality itself. Not the technical history, someone wrote a technical history or not. It's what are the kinds of technicities at work. I really get tired of someone classifying something as technical or non-technical, because if that's the work that's going on, then the work isn't at the appropriate high level that historians of mathematics almost uniquely do. So, as I said, well, I've already gone ahead of myself. I loved this, so I have a picture of Reinhardt talking to us yesterday, and he says, the preference for pure mathematics among the Bourbaki generation of Hardy and the frequent reference to Jacobi's performance of the honor of the human spirit have to be explained historically as well. Yes, 100%. That is our job. If we take them for granted, we are not doing our job. Now, how does that get us back to automatic proving servings and machine learning today? I don't know enough about the stuff of today, and I'm not going to pretend to. But what is very clear is that we have to get away from any kind of history where we treat the aids for doing mathematics as somehow failing to grasp the essence of mathematics. And this is what I've already said before, that poor history is a poor substitute. And that is really undermined so much of what the field has done. But I want to focus on something I said at the beginning, that the failure to produce things that automate mathematics, just as the failure to logicize mathematics, or the failure to fully axiomatize, or the failure to have formal proofs, all of those are failures in one sense, but they produce entirely new forms of practice that are remarkable and extraordinary, even if they don't meet their philosophical goals. And this is what we know of the best things of automatic provings. And so here I'm just going to refer to what I take to be the best study in the history of mathematics to guide us as we collectively deal with this. And this is Steph Dick's great paper based on her dissertation on aftermath. It's like 10 pages long. And it's about an automated reasoning assistant in the 60s and 70s, which was premised on the idea that the intuitions are only human, so it assumes human uniqueness, but that humans can get help. And what Steph does, and it's called Aura, and she writes, and she does this very concretely, and so I'm not giving you the empirical stuff, and I wish she was here. She writes, Aura turned out not to be merely the passive receptacle of that image of mathematics. The very notion of insight, intuition that the Argonne team cordoned off of the human were reconfigured through extensive programming for and collaborating with Aura. So even a computer group that holds to what I think is a very problematic assumption of human uniqueness, even attempting to do that, produces something interesting and new. And then she takes that in a methodological way. And this comes back to images of mathematics. And she writes, the new images of mathematics open countless doors for historians of science to involve themselves with mathematics, to trace the negotiations between even the most theoretical of knowers and the material tools, non-human assistants, and unconventional colleagues, even the ones clothed in electrical circuits, solder, dials, punch cards, core memory planes, wires, and thousands of printed clauses. Amen. Our previous speaker has recently written in a wonderful introduction to a set of papers that our instruments of calculation change the mode of production of mathematical knowledges. Bravo, right? This is the work we need to do. Okay, so I'm going to end with, well, I promise that I hope I've shown you that in some ways that the history of math is of interest to AI, and AI is of interest to history and philosophy of math, both as a subject in its own self and as something that helps us think better about any of the things. And I just want to end by going back to, unfortunately, I missed the Leibniz and Newton conversation because I was stuck in Newark. But I want to go back to the 17th century. And a certain figure whose name is probably not allowed to be said in this room because of Isaac Newton wrote that as human beings, we needed a fila meditandi, a quote, sensible and crude method, but assured of finding truths and resolving questions of given things. That is, we needed algebraic notation. A fully artificial thing that is not human thought is a radical thing that is rejected by other kinds of people. He writes, for whoever would diligently consider the nature of our mind, that although we have an idea within us, ideas of things remote from the senses, we cannot pin down or devote attention to the knowledge of these things unless certain sensible marks approach them. Names, characters, representations, analogies, models, logical connections, and consequences. This is the defense of the introduction of a technology, but it happens to be writing rather than, and it's in a theological treatise, but Leibniz is good on it. So his example, in the midst of him developing his calculus, is actually an example that shows this. And what is it? It's solving an equation in 4 unknowns. And he says, if you try to do this with the wrong technology, it's going to cause horrible confusion and demand immense labor. So he introduces a notation with artificial fictional numbers, what we would consider to be indices. And why? He has to defend it, because it's not a given in time. It expresses exactly the varied order and relations among quantities and characters so that immediately at first glance it appears that certain known letters will pertain to an unknown quantity. In other words, far from this just being a descent of Viet discovering this, of what exactly, it is precisely a spatially understood technology for limited human beings with existing epistemic capacities by which mathematics can be developed. That it is this needs to be understood in the history Klein puts us in, and not in a Whiggish history that treats this as essential to pure math. He's not the only one. Our local boy, Babbage, wrote something extremely similar in his attempts to reform notation away from the horrible notation of dear Newton, and uses almost the same language. The readily they will be caught as at a glance. But this is going to be the very end. The interesting thing, that conception of how one ought to write polynomials in particular, leads him quite precisely to the most deep thing that happens with the analytical machine, an understanding of the separation of what he calls combinatorial operations, formula, and data, and the creation of the very first instantiations of what will later be called loops. In other words, by actually attending much more carefully to the material foundation, we understand far better those ideational things that are important, so that tools are not just incidental, but constitutive of mathematical activity, and indeed constitutive of its diverse forms. Okay, thank you all.
Thank you, Matt. Terrific. Questions?
Thank you. Perhaps a very naive question, but at several points in your talk, you said that the efficiency of data was unimaginable, unthinkable for mid-20th century logicians, computer scientists. So wasn't that, in a way, Venus' dream with the cybernetics? How does that fit in your story?
Well, I'm kind of a cybernetics skeptic, to be honest. I mean, I think it's been given undue weight in the history of computing, but to take your point, there is no question that models of information exchange come to be enormously important. And in particularly, a tradition that I haven't really evoked here, but a tradition of the production of lots of independent agents communicating and working together that's most connected to Selfridge in the early days is definitely a sort of part of that. Now, neural networks have some connection to sort of cybernetic things, but neural networks become, both in terms of initially hardware and then later in their technical development, really quite removed from cybernetics. But I do think there's another connection, which is that and people have recently been noting this, the sort of high moment of, say, French structuralist thought in people like Lévi-Strauss and in Foucault are no doubt participating within a broadly sort of structuralist understanding of the preconditions of knowledge, which are deeply rooted in cybernetic discourses. So, so to tell this story in its full robustness, one would need a much richer story of the early history of neural networks, the relationship to various kinds of sort of high modernist thinking, and other sort of things. I mean, a third answer would be that, you know, Wiener himself gives such a radically different understanding of the history of science in the middle of, that is both wrong but normatively powerful. So, like I said, I somewhat think that cybernetics has been overplayed in the history of computing, but nonetheless, there's a lot of work to do. Yep.
So, Michael, and then Troy.
Thanks very much for this, Matt. One thing I really like about the way you framed this whole run of the talk is how it turns our attention almost away from the history of mathematics and toward the sociology of valuation. So you have that quote from Wilkes that you framed in the beginning. There's a constant thread and theme of people talking about technologies and prospects being overrated or underrated or misrated. And one thing that I think is very important about that sort of just beneath the surface insight of this presentation is a theme that also comes out in your work on Babbage, which is that often what is most historically decisive is how people misunderstand and misevaluate technologies that they don't have an immediate grasp or tactile familiarity from. So I wonder to what extent you would wish to invite us to turn away from mathematics as our focus and to press our interest into more of these questions about how things are valorized and evaluated and misunderstood?
I guess I would just push back and say that those things, there's an illusion that they're distinct.
Okay.
Because if we want to understand different social groups, it's not just going to be sociological factors. And if we were looking at epistemological values, we're going to end up looking at pretty dramatically different understandings of what science and mathematics are. So my favorite example of this, and a lot of this came out of my collaboration with someone who was trained as a physicist, ended up in applied math, and is now the chief data scientist of the New York Times, and so has lived through a lot of different worlds of rigor. But Leo Bremen, who I mentioned, writes this paper on the two cultures of statistics. And it is at once sociological. And he says at that time, 95% of the statistical community is committed to Fisher-Neyman, essentially. And there's a small that are the people who he thinks is algorithmically based, and most of them are in industry or in the intelligence world, and they realize there are many more problems, and there's a balance that is to be sought. And so that sociological question is real, but it also involves at once recognizing different epistemic standards, but also the tools and training that are necessary to use them. So and one of the things I think historians of mathematics can do when we're not being Whiggish is, especially those of us who've experienced, say, early modern mathematics or ancient mathematics, is if you don't take it for granted that, like, you needed Weierstrass, that there are multiple forms of rigor, all of a sudden the world is open to you to analyze. Like, we actually know how to do this. And I think it's really, but it has to be in conjunction, as it were, with values and materialities. And there's no reason we can't do all those things. That's a wonderful question. You try, you have. It's 23 seconds, okay.
It's sort of similar to Michael's question, but prompted by this quotation that you had from McCarthy there, that you characterised as being wasn't entirely wrong, or indeed entirely wrong. I was wondering whether, at that time, McCarthy did not have access to the kind of hardware that would have been necessary to properly do the kind of empirical data-based research that happened to emerge later. And is it possible that McCarthy had some kind of understanding of that and wanted to justify his chosen research program, into which he was for pragmatic reasons, but through an epistemic justification?
Okay, I think it's absolutely the case that McCarthy didn't have access, and people like Shannon, who knew what was going on at NSA, it's not accidental. Like, the charts in the mathematical theory of communication are almost reprints of things from NSA publications on physical cryptography. So Tukey knew and Shannon knew what was going on behind the fences. And so they knew something about data infrastructures and what could be done with them. So yeah, that's certain right. But McCarthy, he's very committed to a really robust sense of mathematics. And he embeds, it's easy to make fun of him in all sorts of ways, but like the production of Lisp is an amazing achievement, right? And the fact that then they spent decades producing sort of like, databases of common notions, it seems kind of ridiculous. But I think so in other words, there's an epistemic understanding. We can understand some of the positions of it. I don't think it can be purely instrumentalized. I mean, it can be reduced to some sort of, because you can understand different kinds of communities. But you're absolutely right. Most of the world didn't know what was going on. And they learned about it in weird ways, like the Bayesian analysis, which explodes both at Bletchley and in Arlington. No one's doing this. And then John Good starts publishing about using Bayesianism in biology. And all he's doing is he's taking his cryptographic papers and rewriting them about biology. And then the philosophers of science get excited decades before statisticians do. So there's a lot of stories like that we still don't know. Anyway, another wonderful question, but my time is, gosh, I have violated all that is holy, and Isaac Newton's gonna come and hang me for counterfeiting.
I stole a minute at the beginning for the commercial. Anyway, thank you very much.